All right, so let's look at this review material where you are to fill in the blanks with however many of these terms can apply. We have local max and min, we have absolute max and min, none or cannot be determined. And these questions are presented in multiple ways. So, number one, we have a table of values that give uh, we have a table for a function f. The function is continuous, and that's important. Function's continuous on 0 to 5. We have f prime, and f double prime. And we are trying to determine what's happening at 0, 2, 4, and 5. Okay, so 0 is at an endpoint. Because it's at an endpoint, it cannot be a local max or min. It can only be absolute. And so I'm looking, and at 0, we'll see my function. This may be good to try to sketch this out a little bit. So I have my y-axis, I have my x-axis, and I'm going from 0 to 2 to 4 to 5. And I start at the point 0, 0. At 2, I'm at the point 2, 4, and that's my highest value that's given in the table. At 4, I'm at the y-coordinate of 1, and at 5, I'm at a y-coordinate of 2. So I plot those points because I know those. Now the derivative and the second derivative will tell me increasing, decreasing, and concavity. So from 0 to 4, we are increasing because the derivative is positive. Then we decrease, and then we increase. And then my second derivative being negative means concavity. So we're concave down, concave down, concave down, and concave down some more. Wow, this thing's always concave down. That's interesting. At negative 4, notice the derivative does not exist on a continuous function. That is most likely a cusp. This first question may have the most to think about. That is most likely a cusp because the derivative fails to exist. So looking at what I see here, I'm thinking we're going to do this. I'm going to make this kind of dotted because it's just kind of thinking. I'm increasing, and we are concave down from 0 to 4. And then we increase while concave down again from 4 to 5. So I'm looking at something kind of like that. And so at 0, that will be the absolute minimum. It is not a local because it's an endpoint. At 2, my function increased and then decreased, changing at 2. So that is definitely a local min. Now, is it also an absolute local min, a local max? Is it also an absolute max? And I believe it is. What is wrong here? Absolute max. There. Because there are no other critical numbers except 4 is a critical number, but 4 is definitely less than f of 2. And my right endpoint is not as high as f of 2. So this is a local max and an absolute max. At 4, my derivative changes from negative to positive at a critical number. And so that is a local minimum. Now, is it also an absolute minimum? And it is not, because I definitely know that at 0, my function is lower than it is at 4. And then at 5, that is an endpoint. So the only thing 5 could possibly be would be an absolute max or a min. The absolute min and absolute max have already been claimed. 5 is not as high or low as either one of those. So 5 is none of those. So there are your answers to number 1. Number 2, my head's blocking the problem. Not really. Okay. Let's see. F is continuous, has its only critical number at 2, and f double prime of 2 is negative, which means the function is concave down. So we have a critical number at 2, and my function is concave down at 2. The only way that could happen, concave down at a critical number, is if you have a maximum. Now the question, is it local and absolute? It's definitely a local. It's definitely going to be a local max because it is a critical number where the second derivative is negative. That's your second derivative test. Is it an absolute max? And yes, it has to be, because the only way it wouldn't be an absolute max is if the function, the continuous function, turned around and eventually went higher than that point. And I know it cannot turn around like that, because if it did, it would create a second critical number, and this is the only critical number. So the fact we know there are no other critical numbers tells you that this function cannot turn around and get any higher. So this is a local max. It is also an absolute max. Okay, so that brings us to number 3. F prime of 3 is 0. So at x equals 3, we have a slope of 0. The second derivative is 1. That is greater than 0, which means we are concave up. So we have a slope of 0 while we are concave up. So this is very similar to number 2. A slope of 0 while concave up. And so that would definitely create a local min. Now the question, is it also an absolute min? And this time, there's nothing saying that this is the only critical number or that the function does not turn back around. It is very possible that this function could turn around and get lower than that 1 point. And so in this case, this is a local min, and that's the only thing we can say with confidence. Might be an absolute, but we don't know that with certainty like we do with number 2. Okay, number 4, we have a graph. This is the derivative. Always pay attention. If you are given a graph, always pay attention to what the graph represents. This is the derivative. And this function, or this question, is asking you about what's happening at 4, 0, 5, and 2. I don't know why I didn't put them in order. Okay, so x equals 4 is right here. And at 4, I can tell that the derivative is equal to 0. So it is a critical number. And I can tell that my derivative is negative before 4 and positive after 4. So my derivative goes from negative to positive. That is the definition of a local min. Now the question is it also an absolute min? And yeah, we can say that on this interval, and I probably should have specified only looking on the interval 0 to 8. So I'm going to add that to this question. We're looking at 0 to 8. And I can see that my derivative is negative and then my derivative is positive. That means that while I don't know what this function, where this function is, I do know this function is decreasing on the interval 0 to 4 and increases on the interval 4 to 8, which means that that minimum is the lowest point on the function on this interval. And so this is also an absolute minimum. Okay, at 0, that is an end point, and an end point could be a max or a min. And so, like I said earlier, I know that my function decreases. So we start at x equals 0, and we decrease to x equals 4. And then we increase after that until we get to 8. And so we increase until I get to 8. The question is, do we increase a little? Like, do we increase a lot? Do we increase a little? How much do we increase from 4 to 8? Because the amount of increase from 4 to 8 and the amount of decrease from 0 to 4 will determine if that left endpoint, and there's our ice maker, is higher or lower than the right endpoint. And that's a little bit of a complicated question. So I may, while I've kind of talked about this a good bit, I'm going to hold off on that question. We'll talk about that in just a minute. Let's talk about these other ones. At x equals 5, so here's x equals 5. Oh my goodness, f prime of 5 is not even 0. F prime of 5 looks like it's about 2/3, maybe. That's not even 0. If the derivative is not equal to 0, then it can't be a max or a min or anything. So that's none of these. And same thing at f prime of 2. While at 2, that is a minimum of the derivative, f prime of 2 is negative 2. That's not even a critical number, so it cannot be a max or a min. And so none for both C and D. And so now back to what's happening at x equals 0. And what we established was that I need to know how much we decrease from 0 to 4 and how much we increase from 4 to 8. And this is a relatively new concept because this is getting into accumulation. The amount that a function decreases is equal to the area under the derivative. The amount that a function increases is equal to the area under that derivative. And so from 0 to 4, this is a semicircle. So the amount decrease, that's an E, on 0 to 4 is equal to, and that's half the area of that circle. So 1/2 pi r, which is 2 squared, and that ends up being 2 pi. So we decrease 2 pi, and then the amount increase on 4 to 8 is going to be the area of that triangle, which will be 1/2 the base, which is 4, and a height of 3, which is 6. So we decreased, whoa, what is that? So we decreased 2 pi, which is approximately 6.28, and we increased 6. So what I know now is that I started from some point, I decreased 6.28, and then I increased about 6, which means this point will be higher than my right point. So that means that at x equals 0, we finally have our answer. At x equals 0, that is our absolute maximum, because the area under the derivative tells you how much we increased or decreased. That may be the hardest one. I said number 1 might be the hardest one, but I think I'm changing my mind. All right, let's see, move my head out of the way. Okay, so we have a continuous function. Its only critical number again, so this is the only critical number, is at 5. And we know that f prime of 4 is -3, f prime of 6 is 7. And so this is one that we can do the number line with. I have a number line for f prime. And f prime of 5, that is our critical number. Now, I'm going to write critical number. I'm not going to say this equals 0 because critical numbers could be a cusp. But what I do know is that on the left side of 5, when I plugged in 4, my derivative was negative. When I plug in 6, they tell you that the derivative is positive. And because this is the only critical number, I know there cannot be a sign change between 4 and 5, because if there was a sign change, that would create another critical number. So my derivative changes from negative to positive. That means my function changes from decreasing to increasing. So this is definitely a minimum, and it's definitely a local. Is it also an absolute? Yes, it is, because again, this is the only critical number. So this is a local and absolute minimum. And I know the function does not come back and get lower than this one, because that would create a second critical number, and there is not a second critical number. And so that brings us to number 6. We have a function that is differentiable on -2 to 5. Differentiable does also mean continuous and has the following properties. My derivative is positive from -2 to 2. My derivative is negative from 2 to 5. And my second derivative is negative from -2 to 5. So I'm going to try to sketch that. -2 to 2 to 5. My function will increase from -2 to 2. So I have some starting point. I don't know where, but I will increase from -2 to 2 and then decrease from 2 to 5. And I will be concave down the whole time. So increase, decrease while concave down. And so let's think about that. At x equals -2, that is an endpoint. So the only thing it could be is an absolute max or min. It's definitely not an absolute max, because I can tell that x equals 2 is going to be my highest point. The thing is, I don't know if it's an absolute minimum, because there's no information to tell you how much we increase or decrease. We only know that we do increase and that we do decrease. It is very possible for me to satisfy all this information with a function that looks like this. I could also satisfy it with a function that looks like this. And I can satisfy this information and make my left endpoint the minimum, or I can make my right endpoint the minimum. And because of that, we don't know. This cannot be determined. Can't be determined at -2. Could be a max, could be a min, we're just not sure. What about at x equals 2? That one is our absolute max. And at x equals 5, again, can't be determined because we don't have enough information to know the amount of increase or decrease on those intervals. I think 7's the last. Nope, there's an 8 also. All right. So we have 7 here. So we have this function g is defined here. It is known that f of 2, f prime of 2 is 4, f double prime of 2 is 6. And the question, we have one about g and one about f. Let's answer the one about f first because, well, let's see. I can't decide. What do I want to do, f or g first? Well, I do know this. This is an integral defined function. And usually when I see one of those, I will immediately find its derivative. The derivative of that would simply be f of x. And so what does g have at x equals 2? Okay, well, for part A, in order for g to have a max or a min, g prime of 2 must be 0, and g prime would equal f of 2, and that is 0. And so f2, so it is a critical number, so it could be a max or a min. And then we can determine local max or min by the second derivative, and g double prime of 2 is going to be the same as f prime of 2. I just did the derivative of both of those, and f prime of 2 is given. That is 4, which is a positive value. So if you have a critical number where the second derivative is positive, that means you are concave up. This is definitely a local minimum. And do we have enough information to determine that it's the absolute minimum? And no, we don't. We don't have any information for anywhere on this graph except specifically at 2. This function could be wavy. There could be asymptotes. Who knows what's going on? So local minimum is all we can say for A. And for part B, we can say fairly quickly that f has none of these at x equals 2 because f prime of 2, which is explicitly given to you, is 4, which is not equal to 0. For something to even consider being a max or a min, has to be either an endpoint for absolute extrema or the derivative must be 0. And we don't have either of those cases for f at x equals 2. And so that brings us finally to number 8. And this is the only one of all of these that gives you an explicit function. And so you are determining extrema. So we will start by finding the derivative. That'd be 2/3 x to the -1/3. And I encourage you, when you start doing algebra, to get rid of negative exponents. And if you are finding a max or min, you start by setting the derivative equal to 0, and a fraction equals 0 whenever the numerator is equal to 0. So technically, it's not technically, there is no solution to that equation. However, but I can tell that if I were to plug 0 into my derivative, I'll be dividing by 0. And that is against the rules of math. So you always need to look out for domain situations. So f prime of 0 does not exist, and f of 0 is 0 to the 2/3, which is 0. That is a defined point on the function where the derivative fails to exist. Therefore, x equals 0 is a critical number. And if you have a critical number, it's possible that that critical number is a local max or a min, and I'm going to determine that by doing the first derivative test. 0 made my derivative fail to exist. Whoops, that's not what I meant to write right there. This number line represents my derivative, and I'm going to plug in -1 and +1 to my derivative. And remember on the AP exam, number lines are 100% invisible. So I need to actually write down that f prime of negative 1 is going to be 2 over 3 times negative 1 to the 1/3. That will end up being negative. F prime of 1 would be 2 over 3 times 1 to the 1/3. That will give you a positive result. If a derivative changes from negative to positive, that means that x equals 0 is a local minimum because f prime changed from negative to positive at x equals 0. So we definitely have a local minimum. Is this also an absolute minimum? And the answer is yes. It is also absolute because this is the only critical number. We did the algebra to find all critical numbers, and the only critical number we found was x equals 0. And if you were to graph f of x equals x to the 2/3, it actually looks like this. It's going to come down to 0, 0. We know that f of 0 is 0. And if you were to dive into the second derivative, we are concave down to 0, concave down after. We already know the function decreases and then increases. It looks kind of like the seagulls you drew in 3rd grade flying off into the sunset. So we have a cusp that is an absolute minimum as well, and we are done. And that was a lot of information. Hopefully it made some sense.